All right. Hi, everyone. Thanks for coming. I'm going to get started by going over the 20 questions here. So the first exam was really good. Well done. So keep up the hard work. And basically, get rid of this. Um, the second exam is very similar to the first exam, with the only difference being the material that it's on. But it's still 21 questions. You still get 70 minutes. It will take you a little longer than the first exam because there are math problems. So just be prepared for that. I don't know why my email keeps popping up here, but it's annoying. All right. So hopefully that'll stop at some point. Or it'll just pop up every email I got today. Anyway, so let's look at these questions, and these will be similar to the exam questions. It says 2 samples of potassium iodide are decomposed into their constituent elements. The first sample produced 13 grams of potassium and 42.3 grams of iodine. If the second sample produced 24.4 kilograms of potassium, how many kilograms of iodine would it produce? So this is essentially a law of definite proportions question. So when we were doing this one, we want to look at the mass of K in sample 1 is to the mass of I in sample 1 as the mass of potassium in sample 2 is to the mass of iodine in sample 2. And again, this is called the law of definite proportions. It's essentially just a proportionality. So in this case, in sample 1, we had 13 grams of potassium. So the mass of K, potassium's K, is 13.0 grams. The mass of iodine in the first sample is 42.3 grams, equals the mass of potassium in sample 2 is 24.4 kilograms, and the mass of iodine in sample 2 is mass I2. That's what we don't know. All right. So what we're going to do is cross multiply these two and then this one. And then, so basically cross multiply these two numbers and divide by this one. And when we do that, the mass of iodine in sample 2 is equal to 79.4 kilograms, which is choice letter C here. Okay, so this is the law of definite proportions, which is part of understanding where how they came up with atoms and the periodic table. So in the next question, it's more of the same. So I'm just going to move this up like this. All right. It says calculate the atomic mass of gallium if gallium has 2 naturally occurring isotopes with the following masses and abundances. So in this case, we're looking at how they find the numbers on the periodic table. You're never going to do this except in this chapter at this time, because this is what the periodic table does for you. So gallium-69 has a mass of just less than 69 because when you squish a bunch of positively charged protons together, that costs you mass, and because of E equals mc squared, this mass is a little bit less than 69. And gallium-71 is the same, it's just a little bit less than 71. And if we were to take a naturally occurring sample of this, we would find that 60.11% are this one, and 39.89% are this one. So to find the average atomic mass is much like you find your average in this class. 25% of your grade is the lab, 40% of your grade is the 5 exams, 25% of your grade is the final, so on and so forth. So we want to take a weighted average. So to take a weighted average, we need to take the mass of the first isotope, 68.9256 AMU, or gram if you prefer, times 0.6011. So we need to convert this to a whole number, not a percentage. So we divide it by 100. And then we want to add it to the other one, 70.9247 AMU times 0.3989 as not a percentage, but divided by 100. And when you do that, what you find is that it's 69.72 AMU. And if you look at a periodic table, this is the molar mass of gallium. So when you look on a periodic table for molar masses, this is where they come from, as you're probably aware, because you did problems like this in the homework. All right, the next one says, what is the classification for this reaction? So we have Fe2O3 plus 2Al yields Al2O3 plus 2Fe. For those of you who are interested, oh no, this one isn't. Yes, this is the thermite reaction. All right, so it uses aluminum powder and rust, and this is what we have here. This is a single displacement or a single replacement reaction. In this case, aluminum, which has an oxidation state of 0, is replacing iron. So aluminum is now with oxygen, and now iron is by itself. So iron goes from 3 plus to 0, aluminum goes from 0 to 3 plus, and that's how this reaction works. This is called a replacement or a single replacement reaction. Okay. The next one is how many moles of N2O4 are in 76.3 grams of N2O4, and then it gives us the molar mass. And I should have mentioned, if you have any questions at any time, just stop me, all right? Just put it in the chat or just talk. Just stop me, and I'll try to answer whatever question you have. It says how many moles of N2O4 are in 76.3 grams of N2O4, and then it gives us the molar mass. Well, in order to do this, what we need to do is take our 76.3 grams of N2O4 times, we want to put the molar mass on the bottom. So the 92.02 grams of N2O4 on the bottom, so that grams will cancel out. And on top, this is grams per mole, so we put the 1 mole of N2O4. And when you do all that math, multiply by the top, divide by the bottom, what you find is that there's 0.829 moles of N2O4, which is choice letter B. All right. Number 5 says, how many molecules of N2O4 are in 76.3 grams of N2O4? So these look like almost the same question, but they're really not. So I'm going to move this up a little bit so I have some space, and then I'm going to put it here. So when there's more than one conversion, as you've probably seen from the lectures, I like to use a plan of attack. So in this case, I can't convert directly from grams to molecules, but I can convert from grams to moles, and then once I have moles, I can convert moles to molecules. Okay, so in order to do this, the first step is exactly the same as in the previous question, and you could actually, because they're the exact same in the two questions, you could just use your answer from this to figure this out, but I'm not going to do it that way because it's not going to be like that on the test. So here we have 76.3 grams of N2O4. Times, we want to convert it to moles. We again put the molar mass on the bottom, 92.02 grams of N2O4, so that grams cancel out. And we put the 1 mole of N2O4 on the top. Then we want to convert it to molecules. And here's where we use Avogadro's number. So remember that 6.022 times 10 to the 23 molecules of, in this case, N2O4 equals 1 mole of, in this case, N2O4. So where do we want to put these things? Well, I want moles of N2O4 to cancel out. So I'm going to put 1 mole of N2O4 on the bottom, and the 6.022 times 10 to the 23rd molecules of N2O4 on the top. Multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. Make sure you're punching this in your calculator correctly, especially if you're dividing by it. If you're dividing by this, it's order of operations. It's easy to get this messed up. So you got to use the EE key or the EXP key, depending on the brand of calculator you have. I discussed that in the video. And when you do all this math, you get 4.99 times 10 to the 23rd molecules of N2O4, which is choice letter A, it looks like here. Any questions on that? All right. So the next one says, In this reaction, what is the correct coefficient for sodium chloride? So we have lead-2 nitrate reacting with NaCl to form PbCl2, lead-2 chloride, and sodium nitrate. Now, the trick to balancing these things is, in this case, it's not a big deal because you only have one polyatomic ion, but if you have multiple polyatomic ions, the trick to balancing them is to make the whole polyatomic ion balanced, not N and O. All right. So in this case, we have one lead on this side, one lead on this side. We're good. We have two nitrates on this side and only one nitrate on this side. To fix that, we put a 2 here in front of sodium nitrate. So we now have two sodium nitrates, which means we have two nitrates on this side and two nitrates on this side. Well, if we look at Na, if we need two sodium nitrates, we need two sodiums. So we need two NaCl. And that'll give us two Cls and two Cls. We're good. So the answer here is B because it asks us for what goes in front of NaCl, sodium chloride. So we need to put a 2 in front of it in order to get it to balance. Number 7 says, calculate the mass percent composition of sulfur in aluminum sulfate. So in order to do this, the mass percent composition is the part divided by the whole. So the mass percent is equal to the mass of S divided by the mass of Al2SO4 3. Okay, so this is basically what we need. And then because it's a percentage, we need to multiply it by 100. Now the trick is, well, how much of this do I have? I have to make an assumption about the amount of this I have, right? Because this is a property where the amount matters. If you have 1 gram of this or 1,000 grams of this, the amount of sulfur and the amount of aluminum sulfate are going to be different. So what you have to do here is assume that you have 1 mole. So if you have 1 mole of this, how many moles of sulfur do you have? You have 3. So if you go to your periodic table and you look up the molar mass of sulfur, you're going to find that it's 32.07. So what you need to do is take, for the mass of sulfur, 3 times 32.07 grams, because 1 mole of this contains 3 moles of sulfur. And then for the bottom, you essentially want the molar mass of aluminum sulfate, which happens to be 2 aluminums plus 3 sulfurs plus 12 oxygens, or you can just look it up. It's 342.15 grams. All right. Sorry, I don't know if you can see that. So now we need to take that and multiply by 100. And when we do that, we get 28.12%. All right, so 28.12%, which is choice letter A. All right, moving along. It says, what is the empirical formula for C6H12O6? C6H12O2. Sorry. So here we need to find the common denominator. And this is wrong on the answer key, okay? The common denominator here is 2, all right? I thought it was glucose, C6H12O6. So the common denominator is 2. We can divide this by 2 evenly, this by 2 evenly, this by 2 evenly. When we do that, that becomes a 3, that becomes a 6, and that becomes a 1. So C3H6O, choice letter A. Okay, on the answer key, it says the common denominator is 3, but the common denominator is actually 2. All right, number 9, it says determine the empirical formula for a compound that contains carbon, hydrogen, and oxygen. It contains 52.14% carbon and 34.73% oxygen by mass. Now this is very similar to the lab that you did, but what the interesting thing here is we have percentages. Remember from the previous problem that empirical formula is the simplest ratio of moles. Well, how do we convert percentages to moles? The truth is we assume that we have 100 grams. And if we assume that we have 100 grams of this compound, it means that we're going to have 52.14 grams of carbon because it's 52.14%. So if we have 100 grams, we have this many grams of carbon. And we have 34.73 grams of oxygen, okay? Now, we have to figure out how many grams of hydrogen we have. Well, in order to figure out how many grams of hydrogen we have, we take 100 minus this, and whatever's left has to be hydrogen. And when you do that math, you find that there's 13.13 grams of hydrogen. But remember, an empirical formula is the simplest ratio of moles. We have grams. So we need to convert each of these things to moles using the molar mass. So in the case of carbon, we're going to take 12.01 grams of carbon on the bottom and 1 mole of carbon on the top. This came from the periodic table. And when I do that math, I find that there are 4.34 moles of carbon. I'm going to repeat this for oxygen, with the key difference being I have to use the molar mass of oxygen, not the molar mass of carbon. So I put 16.00 grams of oxygen on the bottom and 1 mole of oxygen on the top. And when I do that, I get 2.15 moles of oxygen. I'm going to repeat this one last time for hydrogen by putting 1.01 grams of hydrogen on the bottom and 1 mole of hydrogen on the top. And when I do that, I get 13.00 moles of hydrogen. Now, I need to find an empirical formula. An empirical formula is the simplest whole number ratio of moles. Well, to get a simplest whole number ratio, I need to divide them all by the smallest. Said another way, I need to divide this by 2.15, I need to divide this by 2.15, and I need to divide this by 2.15 because that's the smallest of the three. When I divide this one by 2.15, I get approximately 2. When I divide this one by 2.15, I get exactly 1, right? Because they're the same number. And when I divide this one by 2.515, I get approximately 6. So my empirical formula here is C2H6O. All right, and they're all order carbon, hydrogen, and oxygen. So you don't need to know the order of the atoms, but that is choice letter E. Okay. All right. The next one says, consider the following balanced reaction. How many grams of water are required to form 75.9 grams of nitric acid? Assume there is excess NO2 present. And then it gives us the molar masses. So here's how this works. We're automatically told that water is the limiting reagent. Sorry, you can't see that. We're automatically told that water is the limiting reagent and that we want to form 75.9 grams of nitric acid. So by being told that this is in excess, then we know that water is the limiting reagent. So what do we need to do? Well, if we use the balanced chemical equation, we can convert moles of this to moles of water. But we're not given moles of this, we're given grams of this. So this is a stoichiometry problem. We need to go from grams of HNO3 to moles of HNO3 to moles of water to grams of water. All right, so this is basically our plan of attack. Well, we're given 75.9 grams of HNO3 times. We need to convert it to moles. We're given the molar mass, which is convenient, so we put 63.02 grams of HNO3 on the bottom so that grams will cancel out, and it's grams per mole, grams per 1 mole. So we put the 1 mole of HNO3 on the top. Now, something we haven't done to this point. We need to go from moles of HNO3 to moles of water. Always, 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 to convert from moles of one thing to moles of another, we use a balanced chemical equation. In this case, there's a 2 in front of HNO3, and I want HNO3 to go. So I put 2 moles of HNO3 on the bottom, so it'll cancel out. There's a 1, there's no number, but it's a 1 in front of water, so we put the 1 mole of water on the top, because that's what we're looking for. Then finally, we need to convert to grams of water, and you may already have the molar mass of water memorized, but if you don't, it's right here. So we put 1 mole of water on the bottom and the 18.02 grams of water on the top. Multiply by the top, divide by the bottom, repeat until the end. And when you do all the work, you get 10.9 grams of water, okay, which is choice letter C. All right, even more stoichiometry long problem. All right, it says, determine the, I'm gonna put this up a little bit. It says determining the limiting reagent and the mass of nitrogen that can be formed when 50 grams of N2O4 and 45 grams of N2H4. And then it says some possibly useful molar masses. So we have 50 grams of this compound, and we have 45 grams of the other compound. All right, and we want to know how many grams of nitrogen we can form. Well, if we're given a mass of this and we're given a mass of this, we need to figure out which one runs out first. Said another way, we need to figure out the limiting reagent. There's no easy way to do this. The only way to do this is figure out how much of the nitrogen I can make from all of this and how much nitrogen I can make from all of this. Said another way, I want to do the same stoichiometry I just did in the previous problem twice. So I want to go from grams of N2O4 to grams, to moles of N2O4 to moles of nitrogen, and then finally to grams of nitrogen, like so. All right, so starting with 50.0 grams of N2O4 times, I need to convert it to moles using its molar mass, and its molar mass is given here as 92.02 grams of N2O4. On top, 1 mole of N2O4 times, I now need to convert from moles of N2O4 to moles of nitrogen. Remember, moles of one thing to moles of another, balanced chemical equation. In this case, there's no number, so it's a 1 mole of N2O4 on the bottom, and there's a 3 in front of nitrogen, so 3 moles of N2 on the top, times, now I need to convert it to grams of nitrogen. In order to do that, I need to use the molar mass of nitrogen, which isn't given, but it's N2. Don't forget to double it. It's not 14.01, it's 28.02. So I want to put the 1 mole of nitrogen on the bottom and the 28.02 grams of nitrogen on the top. Because it's N2, you have to double it, just like if it was O2 or H2 or whatever, any of the other diatomics. And when I do that, I get 45.7 grams of nitrogen that is formed. Now, the problem is, I don't know if this is how much nitrogen I form because I have this much of the other one. So I need to see if I run out of this first or if I run out of this first. And the only way to do that, unfortunately, is to do all this over again. So in the next case, I want to go from grams of N2H4 to moles of N2H4 to moles of N2, and then finally to grams of N2. So I'm just doing the exact same thing over, I'm just starting with the other chemical. And here they look the same, right? So it's a little bit confusing. So if we start with the 45.0 grams of N2H4 times, we want to convert it to moles, we need to use its molar mass, 32.05 grams of N2H4 on the bottom, and 1 mole of N2H4 on the top. Now I need to convert it to moles of nitrogen, balanced chemical equation. 2 moles of N2H4 on the bottom, and 3 moles of N2 on the top. For the last step, you notice we're doing the same thing. Moles of nitrogen to grams of nitrogen, moles of nitrogen to grams of nitrogen. So we can just copy this down. So we put 1 mole of N2 on the bottom and 28.02 grams of N2 on the top. And when we do that math, we get 59.0 grams nitrogen. So now we know that if we use all of our N2O4, we make this much. If we use all of our N2H4, we make this much. How much are we going to make? Well, how much we're going to make is this much. This is called the theoretical yield. And how do I know this is a theoretical yield? Because it's less. Remember, I figured out how much nitrogen I could make using all of this and all of this. Said another way, after I make 45.7 grams of nitrogen, all of the N2O4 is gone. And if all of the N2O4 is gone, I can't make any more nitrogen. This is called the theoretical yield. N2O4, the chemical, not the 50 grams, is called the limiting reagent. So that gives us both of our answers. So we can find the limiting reagent, which is N2O4, and 45.7 grams of N2 is formed, all right? Because it asks for both in this question. So that's a ton of work, all right? So you have to practice this enough that you can do it relatively quickly to do this. And I understand, you know, if you're not talking the way through it, you can probably do it faster than I can do it as a demonstration, okay? All right, so now we're shifting gears to a molarity question away from stoichiometry problems. It says, determine the molarity of a solution formed by dissolving 97.7 grams of LiBr in enough water to yield 750 milliliters of solution. So in this case, you could do this however you want, just like any of these problems. There's 50 ways to do them, and I only show you one way. But how I like to do this is I want to find the molarity, and I know that molarity is equal to moles solute over liters solution. But I like dimensional analysis. So as you probably see me do in the videos, I do them dimensional analysis like. So what I want to do is I want to go from grams of LiBr to moles of LiBr. And then I want to take those moles and I want to divide by the liters of the solution. And moles divided by liters gives me my molarity. All right. So starting with 97.7 grams of LiBr times. Unfortunately, they didn't give me the mass of LiBr, so I have to look that one up. And it's 86.85 grams of LiBr, just Li plus Br from the periodic table. And on top, 1 mole of LiBr times. Now, dimensional analysis doesn't lend itself well to dividing, but if I put a unitless 1 here, that'll move the moles over. And then I can put the liters on the bottom. Don't forget, you can't put in milliliters. You have to convert this to liters, divide it by 1,000. So I can't put in 750 milliliters. I have to divide it by 1,000 and put in 0.7500 liters. When I do all that work, I find that this is 1.50 molar LiBr. Okay, if you prefer to find moles and then divide by liters, it's the same thing, right? I found moles and then I divided by liters. It's exactly the same thing. All right. Any questions on any of these? Oh, sorry, that's choice letter A. All right. So much different than doing this in person. In person, usually I get lots of questions. All right, let me see if I can find my blank paper here. Oh, there it is. All right, it says, determine the oxidation state of carbon in carbonate. So now we're jumping into redox chemistry. So we want carbon in carbonate. So one thing you definitely need to know is the oxidation state of oxygen. And the oxidation state of oxygen in compounds is -2. As an element, O2 oxygen, it's 0. But in compounds, it's -2. The oxidation state of carbon is unknown. And if you try to look it up on the internet, you will find sometimes it's +4, sometimes it's +2. Occasionally it's even negative. So you're gonna find variable answers. So you can't just look it up. You gotta figure it out for that particular compound. So if we wanna find carbon in carbonate, we do carbon, that's X, that's what we don't know, plus not 2, let me try again, carbon plus 3 times -2. 3 oxygens, each with a -2 oxidation state, equals -2. The overall charge on carbonate is -2. So that's what it's equal to. This is very similar to how you found the charge on the metal for transition metal compounds, so you could put the Roman numeral in. It's the same idea, all right? So carbon plus 3 times minus 2, the oxidation state of oxygen, it's called oxidation state, so you have to know oxygen, equals minus 2. Carbon minus 6 equals minus 2, and carbon equals plus 4, which is probably the most common oxidation state of carbon, but it's not always. So that's basically that. All right. All right. It says, determine the reducing agent in the following reaction. So the reducing agent is the atom that is actually atom or ion that is actually oxidized. So we need to remember our mnemonic device. And our mnemonic device is Leo the lion says Gur. All right. Where Leo is losing electrons is oxidation. Or if you prefer, so it's exactly Leo, losing electrons, oxidation. Gur is gaining electrons is reduction. Again, skip the is if you prefer, if it makes it easier to remember. So we have lithium and iron 2 acetate forms lithium acetate and iron metal. Okay, so we need to determine the oxidation states on these things. First, we need to recognize our polyatomic ion acetate, and acetate is -1. Since there are 2 of them, the iron's oxidation state or charge is +2. All right, lithium is an element. All elements have an oxidation state of 0. All right, this is a compound. So in compounds, nothing has an oxidation state of 0 in your book. In real life, it does, but we're not going to consider those. All right, so this is +2. This is 0. Now, let's look on the other side. On the other side, the lithium is now +1 because it's in an ionic compound and it's a 1A metal, so it's definitely +1. And iron is 0. Now, a common question that I get in my class is, how do I know I can ignore all of this? And the way I know I can ignore all of this is it's acetate on this side and it's acetate on this side. If it stays as the same polyatomic ion, it's not oxidized or reduced. It's not possible. All right. So this changed. It went from an atom to a compound. This changed. It went from a compound to an atom. That's what I'm looking for in these type of redox reactions. Now, this is a little bit oversimplified, but this will work for this class, all right? So we have 0 to +1 and +2 to 0. So now what we need to do is we need to figure out, is it oxidation or reduction? Well, if something goes from 0 to +1, did it gain electrons or lose electrons? It lost electrons, right? It became positive. It lost an electron in this case. So this is reduction. Said another way, lithium is the oxidizing agent. Now, when we look at the iron, it goes from +2. What am I doing? I put this backwards. I said it's losing electrons and it's reduction. It's losing electrons, so it's oxidation. Sorry about that. All right, and it is the reducing agent. It's written right there, and I said it backwards. All right, so this lost an electron, which is oxidation, and it's the reducing agent. Iron went from +2 to 0. That's gaining 2 electrons because it was +2. Now it's 0. It's gained 2 electrons. Gaining electrons is reduction. Said another way, it's the oxidizing agent. The agent is always opposite because if this undergoes reduction, it oxidizes the other thing. So it's the oxidizing agent. It asks us for the reducing agent. The reducing agent is, it's kind of hard to see because I wrote over it, but it's lithium. Okay, so lithium is the reducing agent. Sorry about that. It's written right there and I made a mistake. All right. All right, let's look at the next one. It says, give the net ionic equation for the reaction, if any, that occurs when aqueous solutions of K2S and FeNO3 are mixed. And I'm not prepared here because I don't have my sheet that gives me the solubility rules. So you're just gonna have to take my word for it on the solubility rules. So what we have is, we have K2S aqueous reacting with FeNO3 aqueous, all right? And we wanna see if anything happens when they mix. Well, here, my positive ion is K, and my negative ion is S2 minus. And here, my positive ion is Fe, and my negative ion is nitrate. So this is a double displacement reaction. K has no interest in going with Fe because they're both positive. K is already with S. So the only thing K can go with and form something new is nitrate. Iron is the same thing. It's already with nitrate, so that's not interesting if it just stays with nitrate. That's not chemistry. But it might be able to go with Fs. So the very first thing you want to do is, you want to look at your solubility rules and see if K and NO3 will form an insoluble compound, right? You're looking for something that's insoluble. And what you're going to find is K and NO3 are always soluble. 1A metal is always soluble. Nitrate's always soluble. Then you're going to want to look at FeS. You're not going to find Fe on the solubility rules because it's cation. Your only cations you're going to find, positively charged ions, are the 1A metals and ammonium. So everything else is based on the anion. So if you look up sulfides, you're going to find that in the insoluble section. Sulfides are insoluble, and iron is no exception. In fact, sulfides are one of the things that are used to treat wastewater to make sure that heavy metals don't get into drinking water supply. So this is going to form something that's insoluble, so a reaction is going to occur. The next thing we have to do is, we need to figure out what that is. Well, we have Fe2+. It's with 2 nitrates, so this is -2, so Fe has to be +2. And we have S2 minus. We cross them, we get Fe2S2, but because they're both 2, we cancel it out, and we get FeS as our solid compound. So FeS solid is formed. We have to do the same thing with potassium and nitrate. We have K plus and NO3 minus. We cross them and we get KNO3. Okay, so then we get plus KNO3. Now we need to balance. We have 2 Ks, so we need to do 2 here. We have 1S, we're good. We have 1 iron, we're good. And now we have 2 nitrates and 2 nitrates, we're good. But it doesn't ask us for the overall reaction. This is the overall reaction. It asks us for the net ionic equation. Now, you can write out the whole total ionic equation, which takes half an hour, or you can simply remember that for the net ionic equation, we want the insoluble compound. And what ions were required to make the insoluble compound, the one that's either a solid or a liquid? Fe2+ aqueous and S2 minus aqueous. And you may have to balance it if, in this case, they're all 1-to-1, and we already balanced it up here. So basically, this is our answer, choice letter D. Okay, so remember also that no reaction occurs if both of your products are aqueous. So this product is aqueous, and I should show that. So this is kind of the long way of doing this, but I did want to go through one the longer way. Also note that we would call K plus and NO3 minus spectator ions, because that would also be fair game on a test. Which two are the spectator ions? Well, that would be K plus and NO3 minus. All right. All right, so I definitely should have printed out the solubility rules. All right, but here's another example. It said, which of the following is considered ionic and is soluble in water? Okay, so PbBr2 is definitely ionic. How do I know? It has a metal. All right, if you see a metal, it's definitely an ionic compound, unless it's by itself, right? If it was just Pb, then it'd just be an atom. It wouldn't be a compound. But anyway, this is an ionic compound, but it's not soluble. halides, including chlorine, bromine, and iodine, are generally soluble, but lead is an exception. So this one is ionic, but it's insoluble. C6H12O6. This is glucose. This is a covalent compound. How do I know? Non-metal, 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 no metal. So they're all non-metals. This is a covalent compound. That can't be our answer. KNO3. This one came up in the previous question. Potassium is a metal, so this is an ionic compound. Nitrate's a polyatomic ion. In this case, this is soluble. Potassium salts are always soluble. Nitrates are always soluble. That's your answer. Okay. This is covalent because it's carbon, hydrogen, and oxygen. And calcium carbonate is containing a metal because calcium's a metal, but calcium carbonate, which is chalk, is not soluble in water. Okay, carbonates are generally insoluble, and calcium is no exception. All right, so you can't dissolve chalk in water. All right, next one. It says, how many grams of NaCl are required to make 500 milliliters of a 1.50 molar solution, 1.500 molar solution? So just like the previous example with molarity, there are lots of ways to do this. But what I'm going to suggest we do is, for number 17, we go from liters of NaCl solution to moles of NaCl, and then finally to grams of NaCl. In molarity, with the exception of the dilution equation, the volume always has to be in liters. So we're never using milliliters. So we got to take this milliliters and divide it by 1,000. 500 divided by 1,000 is half, so 0.5000 liters of NaCl. Now we need to convert it to moles. In order to convert from liters to moles, we have to use the molarity. All right, so that's basically what we're going to have to do here. So if something is 1.50 molar, it means that 1.500 moles of NaCl are equal to 1 liter of the NaCl solution. So it's the molarity number of moles per 1 liter. In this case, I want the liters to cancel out. So I put the 1 liter of NaCl on the bottom. I put the 1.500 moles of NaCl on the top. Now I want to convert it to grams. So I have to look up the molar mass of NaCl. So I put 1 mole of NaCl on the bottom, and I put the 58.44 grams of NaCl on the top. And when I do all that math, multiply by the top, divide by the bottom, I get 43.83 grams of NaCl, which is choice letter D. All right. Again, there are other ways to do this. All right. But this is how I like to do these because it looks like dimensional analysis. And it's useful in the next two problems where we're doing what is called solution stoichiometry. But before we get to solution stoichiometry, we do have one in the middle, which is about dilution. It says, how many milliliters of a 0.266 molar NaNO3, sodium nitrate, solution are required to make 150 milliliters of a 0.075 molar sodium nitrate solution? So here we have a more concentrated solution, and we're forming it into a less concentrated solution. This is a dilution. And to do a dilution, we need to use the dilution equation, which is C1V1 equals C2V2. Some of you may have learned it as M1V1 equals M2V2. It's the same thing. C stands for concentration. Molarity is a specific unit of concentration. It works for concentrations other than molarity, so I like this one better. All right, so this is the equation that we want to use. So what is our initial concentration? Well, our initial concentration is the higher concentration, which is 0.266 molar, times V1. What is V1? Well, it doesn't tell us V1 because we want to make 150 milliliters of the less concentrated solution. So V1 is X, or the variable. I'm going to leave it as V1. C2 is the final concentration, the lower concentration, which is 0.075 molar. And V2 is 150 milliliters. because this is essentially an inverse proportionality, okay, you can leave this in milliliters. However, if you prefer to convert it to liters, you won't be wrong. You're just going to get V1 in liters, and then you have to convert it back. Okay, so it's an extra step, but if you in the previous question didn't convert this to liters, you would have got the answer wrong by 3 orders of magnitude. So here, if we do this math, multiply by these two and then divide by this one, we end up with the answer, which is 42.3 milliliters, which is choice letter B. All right, so now we'll get into the solution stoichiometry problems, the last two. It says, how many milliliters of 0.55 molar hydroiodic acid are needed to react with 15 milliliters of 0.217 molar cesium hydroxide? All right. Sorry. So here is the actual question. Okay, I just read it, but here it is. So basically what we know is that this is 0.550 molar. All right, and we know that we have 15 milliliters of this one, 15.00, and it's 0.217 molar. And we want to know how much of this one do we need to react completely with this one. All right, so half the battle here is figuring out what you're given and what you're trying to find. So basically, we know the molar relationship between these. We know that 1 mole of this reacts with 1 mole of this, but we're not given moles of this or moles of this. So we need to find them ourselves. So in order to do that, what we need to do by way of plan of attack is go from liters of cesium hydroxide to moles of cesium hydroxide. Once we have moles of cesium hydroxide, we can use the balanced chemical equation to find moles of HI. If we have moles of HI and we have the molarity of HI, we can convert it to liters of HI. Note that all of our answers are in milliliters, so whatever liters we get, we're gonna have to multiply by 1,000 to find the correct answer. So when we do this, we need to plug this number in liters. Said another way, we need to divide it by 1,000. So we can't plug in 15 milliliters, we have to plug in 0.01500 liters of cesium hydroxide. We now need to convert it to moles of cesium hydroxide. So this is just like a couple problems ago where we were using a molarity to convert from liters to moles. So if this is 0.217 molar, it means for every 1 liter of this particular cesium hydroxide solution, it contains 0.217 moles of cesium hydroxide. So there's essentially 2 things you need to be able to convert to moles, grams and liters. To convert grams to moles, you use a molar mass. To convert liters to moles, you use a molarity, as shown. Now, we need to go from cesium hydroxide to HI. Always, 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 one thing to another, balanced chemical equation. In this case, they're all 1. So 1 mole of cesium hydroxide on the bottom and 1 mole of HI on the top. I recommend writing this, even though I understand mathematically you're multiplying and dividing by 1, you're not really doing anything. Okay, you don't need to plug it into your calculator, but I do put it here. All right. Next, we want to convert from moles of HI to liters of HI. This is exactly the opposite of what we did here. By exactly the opposite, I mean we flip it upside down. But our HI solution isn't the same concentration as our cesium hydroxide solution. Specifically, it's 0.550 molar, which means that there are 0.550 moles of HI in 1 liter of the HI solution. But in this case, I want moles to cancel out. So I want to put the 0.550 moles of HI on the bottom and the 1 liter of HI solution on the top. And when you do all that math, you get a number, which is 0.00592 liters of HI. Answers are all in milliliters, so we have to multiply that by 1,000. That's 5.92 milliliters of HI. Now, if we were doing this in class, somebody would inevitably ask me, can I use C1V1 equals C2V2 to solve this problem? By sheer luck, it'll work for this one, but it won't work for all of them, so I don't recommend it. okay? If the stoichiometry is 1-to-1 or 2-to-2, or if they're both the same, that does work, but I don't recommend it because it doesn't always work. I know they teach that in some chemistry classes. Maybe some high school teachers use that method, but it only works in specific cases. I'm not saying it's wrong, it's just not broad enough. All right, here's an example where it wouldn't work. It says, what mass in grams of AgCl is formed from the reaction of 75 milliliters, let me get it on the screen, from the reaction of 75 milliliters of 0.078 molar silver acetate solution with excess magnesium chloride solution. And then it gives us the molar mass of silver chloride. So we have silver acetate reacting with magnesium chloride to form silver chloride and magnesium acetate. We have a double displacement reaction, and silver chloride's not soluble. Chlorides are generally soluble, but silver is an exception. So we're told that we have 75 milliliters of a certain concentration of this, and we're told that we have excess of this. Said another way, we're told that this is the limiting reagent. And what we want to know is, if we have that amount of this, how much of this can we make? So in this case, we want to go from liters of silver acetate, which is AgC2H3O2, to moles of silver acetate, which is AgC2H3O2. Once we have moles of silver acetate, we can convert it to moles of silver chloride, which is AgCl. Then finally, we can convert to grams of AgCl. So this is basically our plan of attack. It's essentially combining the stoichiometry problem we did in the previous one to the solid stoichiometry problems we did earlier. So in this case, we want to start with liters of AgCl. So we have to divide that by 1,000. 0.0750 liters of AgC2H3O2 times. We now want to convert this to moles. In order to convert from liters to moles, we're going to use the molarity, this molarity. So we put 1 liter of this compound on the bottom, and we put the 0.078 moles of this compound on the top. Times. We now need to convert to moles of AgCl. So moles of one compound to moles of another, always a balanced chemical equation. In this case, we're going to put the 2 moles of AgC2H3O2 on the bottom, and the 1 mole of AgCl on the top. Now we want to convert it to grams of AgCl. So we put the 1 mole of AgCl on the bottom, and the molar mass of the AgCl is here, 143.32 grams of AgCl on the top. And since we're converting to grams, you can't use the C1V1 equals C2V2 anyway. And when we do this, we get 0.838 grams of AgCl, like so. So this took me 52 minutes to go through. I understand I was explaining it, but these problems do take quite a long time. Please make sure you're prepared that you can do the exam in 70 minutes. I'm not saying it's like super time pressured or anything, but you don't want to be trying to look up how to do this while you're trying to take it. You want to practice 2 or 3 of these or 5 of these before you take the exam. My guess is that, if you're here tonight, you don't need to hear this from me. You probably already have practiced it enough and didn't get a whole lot out of this, but that's basically that. Does anybody have any questions?
I have a question.
Sure.
So for this one, how come it's not 1-to-1 with the AgCl and the AgC2C3O2?
Good question. It's not 1-to-1. It's 2-to-2, isn't it? I just made a mistake.
It shouldn't be 2 to 2. Okay.
All okay. Right. Yeah, it's 2-to-2. This should be 2 here because there's a 2 there. Thank you for pointing that out. Does anybody have any other questions about this or anything else in the course? All right, thanks for coming tonight, everybody. Good luck on the test. It'll be available for you at 8 a.m. tomorrow morning, continue until Sunday at 11:59 p.m., just like last time. And you all did awesome on the first test, so I'm confident you're all going to do great on the next test as well. It's super weird for me to teach like this, but I do appreciate all the hard work that you're putting in. So keep up the hard work, and I'll see you next week at 6 o'clock on Thursday. Have a good night, everyone.
Thank you.
Thank you.